So just basically, let's talk a little bit about physical properties. This is a sapling question, number 33. But it's also really important to just think about also like the idea about like dissolves like, essentially. In the context of, in this case, we're going to talk about boiling points, but you could also think about what dissolves in what, and things of that nature. So like dissolves like. So like meaning similar numbers of carbons, right? Like meaning similar functional groups, right? Polar functional groups. If you have heteroatoms like OHs and NHs, you're going to be right similar, right? You have hydrogens bonded to atoms with lone pairs. If you have carbonyl groups, those are similar things too. So if you look at these, what's going to be what's going to have the highest? What's going to maybe have the? I always think when you have a ranking, find the highest and the lowest, and then work your way to the middle. Right? Find the highest and the lowest of whatever you're asking. So maybe the easiest one is what's the lowest boiling point here? What's going to have the lowest boiling point? So it has the least polar bonds, right? When we say boiling point, we're thinking about what? Intermolecular forces, right? So we're thinking about OHs, right? Polar bonds interacting between molecules. So which one of these is the least polar? What's it called? That's called propane, right? Methyl, ethyl, propyl. Yep. So propane will have the lowest boiling point, right? Has the least polar bonds. What would have the highest boiling point? What has the most polar bonds? The carboxylic acid. And what's the name of that carboxylic acid? Propanoic, right? 3 carbons, propanoic acid. So this would be for the lowest boiling point, right? Because of that part, this is going to be 1, have the highest boiling point. Now, what's going to be in between there? We have an alcohol, propanol, and we have an aldehyde, propanal. What do you think is going to have a higher boiling point? The alcohol or the propanal? The alcohol will, right? Again, we're thinking about that OH bond, that polar OH bond. Hydrogen, right? Hydrogen bonding. Can it do hydrogen bonding? Right? Can it do hydrogen bonding? Right? Especially with itself, hydrogen bonding with itself, right? So this would be 2, this would be 3. This OH bond is more polar than this OH bond because this oxygen is also pulling on it. You know the resonance structure that makes this even more delta plus than this, right? It's a more polar bond. That's a carboxylic acid. It's more acidic than an alcohol, so that's why this is 1. This is 2. No polar bonds is 4. Acetyl bond O is more polar than no polar bonds. So that's the ranking. Which of these would be soluble in diethyl ether? 4 for sure. Probably 3. 2 and 1, right? Diethyl ether. We're thinking about diethyl ether. Right? There's no polar OHs, right? It's a good polar organic solvent, but, right? These 2 things might not be soluble in diethyl ether because they can do hydrogen bonding, that OHs. So this is number 38. What kind of reaction is this? Who recognizes this reagent? It's an epoxidation. It's an epoxidation. Right? It's forming the 3 member rings with oxygen. This oxygen right here. Everybody see that? That's the oxygen that gets added. You've seen it like this, or you've seen it called maybe MCPVA. That's a different type of epoxidizing reagent. But this perbenzoic, if you see this OO like this oxygen on the end is the one that gets added. And it gets added across an alkene. Right? So it's a classic alkene reaction. But you needed to recognize this reagent and recognize that that's the oxygen that gets added. Okay? Also, you think you need to recognize the alkene. The alkene starting material is what kind of stereochemistry? Trans. So if it's trans in the starting material, it needs to be probably trans in the product, right? Because this is a 1-step reaction, right? There's no carbocations. So if it's trans to start, it's going to be trans in the product. So the epoxide, the oxygen, hopefully you guys remember doing these. The oxygen it can add that way. Or it could add from the bottom. In this case, what are we forming? We're forming two enantiomers. Well, yep, two enantiomers. Nope, they're not enantiomers. They're mirror images of each other. They're the same. They're the same. There's symmetry. They're the same. So sometimes, if this was an ethyl, it would be different, but these are the same molecule. Sorry. I'll flip it around in your head. Big take-home message. Epoxidation, right? The peroxy acid. Do you see that? And that's the oxygen that adds. If you add something in an alkene and there's no carbocation, the stereochemistry, whether it's cis or trans, stays the same. And then be careful, right, about whether you make enantiomers or diastereomers or something that's the same, right? This molecule of symmetry, it caught me. What is actually the same molecule, right? These two things are the same thing. So be careful with that too. So the answer is not A, because where this molecule is most reactive is actually this oxygen. It's not acting like an acid first. It's actually most electrophilic at this oxygen. So don't treat it like an acid where this pi bond would react with the acid. It's actually, because this OO bond is actually really weak, it's this oxygen that's most electrophilic. It's weird, but that's what's most electrophilic. So that's where this pi bond is going to react with that oxygen first. So that's why it's not A. So this is number 37. This question asks, which of these methods would be best for converting 3-hexyne to Z3-hexene? So first thing they're asking you, do you know something about nomenclature? Right? They want to know, do you know what hexyne is versus an hexene? So what's a hexyne? Hexyne is a alkyne, and then hexene is an alkene. And then Z, do you know what E and Z mean? Z means Z same side, right? So it has to be what kind of addition would you need then to get things on the same side? You'd need a cis addition, right? So this question is about nomenclature, E and Z, and about cis addition. Right? They want to know, do you know how to turn an alkyne into an alkene in a Z fashion? Right? So what do you need to know, though? You need to know some nomenclature. You need to know E and Z, right? And then you need to know at least what ein and een, those suffixes meant. Now, what's the right answer? The right answer is C. The right answer is C. Now, to be fair, if I had wrote Lindlar's catalyst, would that have helped? Because that's what this is. Right? And I'm not sure if this is an old test and people have stopped, most books don't show the barium part. They just say it's Lindlar's catalyst. So now you know that. But even so, you should have still be able to figure it out, perhaps, even if you didn't know what that was, because all the other reagents you should have looked at and been like, well, that's not right. Right? So the first one was sodium borohydride. What does sodium borohydride react with? What have you seen sodium NaBH4? What does it react with? Carbonyls. There's no carbonyl here. Right? You've never seen sodium borohydride react with an alkyne. Haven't seen it. Sodium and NH3 liquid. That's that sea of electrons one, remember? And that makes an alkyne turn into a transalkene. Right? The NH3, when it's in the liquid, that gets you a trans or E-alkene. Right? Sodium metal, lithium metal, sodium or lithium usually it is, sodium or lithium. Right? That gets you that trans or E-alkene from an alkyne. And then D was H2 and platinum. That takes an alkyne and makes it into an alkane. Right? So you should have, worst case, you could have recognized maybe A, B, and D and then be like, well, it must be C. Right? But Now you know if you saw that as Lindner's, that might have helped. And hopefully the newer versions just say that. So number 50, what is this question about? So let's look at the reagents. So what kind of question is this about? What's the first? We recognize these reagents hopefully as something. HBr peroxide. Everybody remember what that means? What does it do? It's a radical, adds a Br on the anti-Markovnikov spot. Right? It's a radical reaction. And it adds Br in an anti-Markovnikov fashion, which means on the less substituted carbon. Right? So if you know that reagent, this problem's done. You don't need to look at the NMR or the mass spec. So if you know that, then you automatically should know that the answer is then A. So A is the right answer. So that reagent helps you do that. Now, so that'd be the first thing I'd look at, like looking at the reagents to hope you recognize those. If I recognize this, what do you see from KO potassium tert butoxide? What is that to you? What does that tell you? What kind of reactions is that involved with? Not SN2. It's too big and bulky. Tert butoxide, right? It's this structure. It's involved with E2 reactions. Right? E2 reactions. This nitrogen, all it's going to do in this case is a SN2. This is going to do an SN2 for some reason. I don't know why they put the nitrogen in there, just to throw you off. Like, they didn't need to do this step. I don't know why that step was there. It was just to throw you off. And it did, right? They were trying to throw you off there. Like throwing that nitrogen in, right, somehow made it about the nitrogen. But you put the nitrogen in, all you do is do an elimination, make a pi bond, let's see, here, and then they actually end up the pi bond ends up over here, because this is one of those reactions that I didn't teach you, Hoffman or Cope elimination. This is one of those reactions we didn't get to. That's okay. This is the key thing if you recognize that, which we did cover. Also, what you can look at here is the NMR or IRs. So if you look at this, C and B both have alkene CHs. Where are alkene CHs at in an NMR? What ppm? If you're on an alkene or vinyl CHs, where are those hydrogens at? What ppm? Between 5 and 6, 4.5 to 6.5. Look at the NMR. Does the NMR have anything that's between 5 or 4 up that high? Nope. So it can't be either of those two then right off the bat. Right? Also, I'm not even looking at the splitting or the integrations at this point, right? I just looked at the frequencies. Didn't make sense. Also, if you look at the mass spec, you see in the very end, you see the two peaks that are the same height. Remember we talked about bromine having isotopes, bromine 79 and bromine 81 of equal magnitude. Remember chlorine is 3-to-1, chlorine 35 and chlorine 37. So that's a good way to tell on your mass spec. If you have the peak at the far right, your largest peak, if the two peaks are equal in height, that tells you there's a bromine in your molecule. That tells you there's a bromine in your molecule. So just by looking at the NMR and IR, I can at least narrow it down between A and D. And then if I actually start looking at the NMR, and I look at the splittings, it should be pretty clear that it's A, just based on the splittings and what the hydrogens are worth, right? So for instance, D has a peak that should be worth 1H, right? If you look at the NMR, there's a 2, a 2, a 2, and a 3, right? So it'd be nice if they had told you 2 H's, right, for the integrations, but they didn't. But you should look at it and be like, well, wait a second. There's 3 that are equal height and 1 that's bigger. If I look at A, I see there's 3 CH2s and 1 CH3. So that must be that. And if I look at D, I see I see 2 CH3s, a CH, and a CH2. So just looking at the integrations, I know that can't work for the NMR too, right? Really simple stuff. Don't get so bogged down, right? And like, oh my God, I forgot the splitting. Like, wait a second. Remember your frequencies. Look at the frequency table and look at the integrations, right? Really simple stuff will help you, right? Eliminate possibilities. But the key here, right? If you knew what the reagent 3 was, this problem's done before it starts. So the keys to this question, number 70, what did it ask? Which pair of reagents are used to manufacture nylon 66 through a condensation polymerization? The key there was condensation. Do you know what a condensation reaction is? Right, what's a condensation reaction? Right, you lose water, or you're generating water, right? You're generating water, not, right? Most condensation reactions, right, we've done, or be it eliminations, or, right, the one major one we did this last with carboxylic acids, with the carboxylic acid and a amine. So here's the two to look at. So A has, right, basically this reaction, you basically is asking you, do you understand how the reagents will react, the answers. So A has an NH2, an amide, right, reacting with an alcohol. What's that going to form? If an amide reacts with an alcohol, that could form an ester, right? Or it could form no reaction at all because amides aren't that reactive. But it's not going to make water. If anything, it make NH3, right? So that doesn't make any sense. The second one, right, has a Grignard reagent with an acid chloride. That's not going to make water, right? That's not going to make water. That might react and make that product, but it's not going to make water. C has two amides, like there as reagents. Do two amides come together and make water? No. And then finally, for D, you have a carboxylic acid and an amine. Those will come together and generate water, condensation reaction. So this problem looks really tough. All they want you to know, all they're asking, the real point of this question is, do you know what a condensation reaction is? And then if you see them, can you recognize it? So that's why it's D. Right? Condensation means you're going to generate water. Only D does that. Now C or B could make the product, right? B could make nylon, maybe, but it's not going to generate water, right? It's not doing it through a condensation polymerization, right? So make sure you read carefully, right? Read carefully those words. Look for those key words in those sentences in those questions. They're there. So 68. What is this question? What kind of reactions are in this problem? Everybody remember what's the first reaction? Going on right here, what kind of reaction is that? It's a Friedel-Crafts acylation, right? That's going to make this, that electrophilic aromatic substitution. So you can't turn a ketone into a carboxylic acid with KOH. So you start with a ketone. What's this next reaction going to be? What? It adds a bromine, but it's an electrophilic aromatic substitution, right? So where is it going to add? Well, then we look at, is a carbonyl, a ketone, is that electron donating, electron withdrawing? Withdrawing, so it's going to direct meta. Right, so I want to know, right, do you understand electron withdrawing, electron donating groups? This is basically electrophilic aromatic substitution problem. So now you're here. And then what does this last reagent do? Who remembers what this reagent does? It reduces. It's the Wolff-Kishner. Right? It reduces, and it turns the ketone, right, just into a CH2. So that was D. Now, let's say you didn't recognize. So I would hope on all my hopes, that you at least knew the first two you should have known for sure, right? That would have eliminated A, right? KOH is not going to turn a ketone into a carboxylic acid. So that should eliminate A. Now you're stuck with B, C, and D. B, I don't know how the bromine got outside the ring, right? So if you knew these two, you knew the bromine and this carbonyl on the ring. Hopefully you knew something about meta. So that leaves, essentially, the answers are B and D. Now, B is fine, but then there's no reason to have that third reagent. And they usually won't have a no reaction type thing. So worst case scenario, if you had no idea what this did, and you got stuck here, you said, well, it's there for a reason. It must be doing something, right? Everybody knows what it does. It makes an imine, and then eventually loses N2. We did that mechanism, actually. You were there. It's on the test, actually. It's in your exam 3. It's on there. We did a whole mechanism on it, so check that out. That gets you to here.